Okay, so I guess we can start. Hello, everybody. It's really a great pleasure to introduce Licia Verde today, our speaker today. Licia is a professor at the University of Barcelona at the Institute of Cosmological Studies. And she's a fellow Italian cosmologist, started her career in Padova to then move to Edinburgh as a PhD student, and in the US, Princeton and Rutgers as a postdoc, where she was part of the WMAP team, and she has very influential papers as a part of this collaboration. She was then a faculty at Pennsylvania, I guess, and then moved back in 2007 as a professor in Barcelona. She's a brilliant cosmologist, I must say, with very wide range of interests from large-scale structure to CMB. And today she's going to talk about what will be the next surprise from cosmology. So, Licia, please.
Thank you. So, thank you for this introduction. You made me blush. Thank you for inviting me to be here. It's a pleasure. I apologize. I got a cold and my voice is what it is. If you can't hear me, please let me know. I'll try to shout and make use of the microphone. What I'd like to talk about today, it's a little bit of a provocative question, but bear with me. What will be the next surprise for cosmology? So we know that cosmology, we've heard that for many years. Cosmology has entered the precision era. We have a standard model. It's the famous LCDM model. This model has very few parameters. With this handful of parameters, it can describe very well all the observation we have of the universe on the largest scales. And it can describe well the origin and the evolution and the growth of structure, etc., and all that. What I want to make you notice is that this model was actually proposed in the 80s and 90s, and it has survived basically unscathed an avalanche of data. And it's one example of this avalanche of data, and I'm sure you're very familiar with this. From observation, this is the map of the cosmic microwave background of the. Most of it is temporal fluctuation, from COBE in 1992 to WMAP in 2003 to the two major Planck release in 2013, and this is my collage to actually show the fact that now there is also a very good map, also the polarization, not just of the temperature, so of also the polarization signal. So you can see how rich the information, how it has evolved over the year, and still that model has survived basically unscathed. And from the large scale structure side, some, a few billions years after we've seen the initial condition of the universe, then we had something like that, right? This was the state of the art in large-scale structure surveys when the LCDM model was being formed. And today we have something like this. This comes from the Sloan tree, where this map here will fit somewhere in that little corner there, and still the model has remained the same. And I like this plot from Dave Schlegel that shows how galaxy redshift survey are increasing of a factor of 10 every 10 years. And in this plot, you see how these different survey scales in terms of the log of the number of galaxies. And if you extrapolate, all linear mode will be mapped by 2043, and all detectable galaxies will be mapped by 2061. So the fact that the LCDM has survived unscathed this avalanche of data, especially the Planck data, and you here had a very, the AAP play a very strong role in the analysis and the interpretation of the Planck data, led some very famous person to actually say, well, we live in a maximally boring universe. Maybe so, but cosmology has surprised us before, so there may still be surprises there. And now I don't want to claim that there will be surprises, but say that I have to bet on a surprise, or the buzzword this day is disruption. If I had to bet, what would that be? Maybe it is a maximally boring universe. That may also be one possible bet. That will be maybe a surprise, because we know that the LCDM model has got some ingredient that we know are effective, and probably they are not the ultimate answer. So among these bets, there will be more sure bets and less sure bets, but let me give you some personal selection. So the first thing I want to discuss about, not necessarily because it's more sure or less sure, but just because I think it's interesting, it's what I call the H0 game. The H0 game, H0 stands for the Hubble constant, or Hubble parameter at redshift 0. It's what I called an end-to-end test of cosmology. And we've been able to start doing this kind of end-to-end test of cosmology only relatively recently, in the past couple of years. And that's why I want to talk about this here. So why it is an end-to-end test? It's because until very recently, we would measure cosmological distance through a cosmic distance ladder that was only getting as far as the supernovae. But now we have been able to extend this ladder all the way through the cosmic microwave background, all the way basically to the initial condition of the universe, all the way through the entire visible universe. And I call this end-to-end test because you want that the value of this parameter that you measure locally agrees with the same parameter that you measure by extending this cosmic distance ladder all the way to the whole visible universe and bringing it back. So in other words, you are trying to thread a needle from the other side of the universe. You have a local measurement, and then you have something that you infer from looking at the last scattering surface, and you are trying to thread this needle from the other side of the universe. So let me go a little bit slowly through this, and the ingredient that we need in order to do this, maximal cosmic distance ladder are standard candles and standard rulers. So I think we know the game of standard candle because it has been around since, at least since the 90s or before. And the idea is that type 1a supernovae are standardizable candles, and they are very good at measuring relative distances. There is a large uncertainty on the absolute magnitude of a fiducial supernova, but the assumption is that after standardization, they all have the same absolute magnitude, and therefore they are really good at measuring relative distances. The way to calibrate the cosmic distance ladder with supernovae is to calibrate it locally with measurement of the Hubble constant in the nearby universe. On the other hand, something that has become possible only after 2005, when the signal was first detected, although at an excruciatingly low signal to noise the first time, is the measurement of the baryon acoustic oscillation. The baryon acoustic oscillation gives us a standard ruler. They can measure absolute distances assuming that we know the value of the sound horizon radiation drag. And this is something that we can measure very accurately by interpreting the cosmic microwave background temperature anisotropy, and polarization helps too. So this allows you to do a cosmic distance ladder, but calibrated at redshift 1100, while this allows you to do a cosmic distance ladder, but calibrated at redshift 0. And the nice thing is that since over the past couple of years, the data for the supernovae and the data for the baryon-acoustic oscillation, first they started overlapping in redshift. Second, they started having a good enough precision and signal to noise that becoming, that is comparable between the two. Now we can play the following game. And the following game is what I call the direct and the inverse distance ladder. Let's see how it goes. So here you have direct H0 measurement. Here you have the supernova, the baryon acoustic oscillation, and the cosmic microwave background that gives you the sound horizon radiation drag or a high redshift anchor, and the direct measurement gives you a low redshift anchor. So the classical cosmic distance ladder goes as follows. You use H0 to calibrate the supernovae, right? But now the supernovae and the BAO overlap and they can calibrate off one another. And now then you can extrapolate this all the way to the cosmic microwave background. That's what I call the direct distance ladder. And the inverse distance ladder is because the cosmic microwave background gives you the high redshift anchor. These high redshift anchors directly give you the interpretation of the baryon acoustic oscillation. These are now calibrated on the supernova, and so you can extrapolate this ladder all the way to redshift 0. So very good. But good ladders always need two good anchor points. And that's what I want to discuss. And that's what I call the trouble with H0. So this is a paper that came out in 2016. So it's a little bit old, but it's still very timely, because only last week there were 2 papers coming out relying very heavily on this paper. So I thought we would discuss this. So we had, at that point, a direct measurement from Licia et al. 2016, which is around 73.2. But the Planck observation of the cosmic microwave background, relying on a lambda CDM model, gives you a number that is more like 78 or 77. Formally, it was 3.4 sigma. So when it goes above 3 sigma, even in cosmology, we should start paying attention. And it can get worse depending on how you analyze the different data, but we'll see. So what's the historical evolution of the measurement of the Hubble constant? H0 doesn't have an exactly spotless track record. This started from the initial measurement of Hubble all the way to the year 2000. But you know, it has been stable since about the 1990s on this scale. What I want to concentrate more is on this. This is from a recent paper from Sylvia and collaborators. So you see from the year 2000 to around here, there are some measurements that hit 73 or 74, and some more cosmological measurement that hit more like 60 something. These are forecasted data. So let's look at this end-to-end test of the universe. This is the direct measurement at low redshift, and these are CMB-based determination of this quantity. In green are actually three different measurements from the time delay distances with lengthening. This is also a geometrical measurement, but the error bars are still relatively large. So do we pass this end-to-end test? Well, at the 3-point-something sigma, right? So let me recast this plot in the light of what we understood since 2016. And this is the way to recast this plot. So here is the measurement from Planck in the lambda CDM model. This is an extrapolation, right? We are assuming lambda CDM model. This is a measurement that actually does not rely on Planck. It just says, let me take the BBN, let me take the D over H abundance. This gives me an estimate, assuming standard early time physics of the sound horizon and radiation drag. And then let me use baryon acoustic oscillation and infer the value of H0. And this came out 2 days ago. It's a similar game, but now done with the DES data. Using, however, a determination of the sound horizon and radiation drag based on CMB data, but done in a model-independent way. And this is where it stands. This is the Licia et al. 2016 measurement, and these are reanalyses of the same data. And this is a way to actually break those data to test for every possible systematic, using near IR only, using a special way to do the parallaxes with the HS0, with the HST that actually improves a lot the PSF of this object. This is the Gaia data release to recalibration of 46 Milky Way Cepheids, and this is the lengths, the 3 lengthings and 4 lengthings from the Holy Cow collaboration. Remember time delay distances. These are 2 papers, but on this scale, the error bar look the same. So do we see a trend here? I think we do see a trend. All these measurements are based on early universe physics, assuming some standard early universe physics, and it's extrapolated to redshift 0. All these measurements come from the late universe and are local measurements. There's no cosmology, there's really no cosmology here. And all these measurements hover around 74. So we had a glimpse of this a couple of years ago, and then we decided to follow 3 avenues without invoking systematics beyond those declared by the authors of the papers themselves. So we decided to allow early cosmology to deviate from lambda CDM and leave unaltered late-time cosmology. We decided to give freedom to the late-time cosmology, but leave unaltered early-time physics, and then see if we could go towards something that is completely model independent. And at that point, we decided to use the latest data that were available back then. There are some more recent data, and these are all these papers that I was mentioning, but the gist of the message is basically the same. So if you want to modify the early universe physics, one simple way to do that is to modify the primordial helium fraction. And that changes the recombination history, affects the diffusion damping and the redshift of the last scattering. And so this is the plot of H0 with the local measurement compared with the Planck plus Planck PAO. And here is with polarization, and this is without polarization. And these are actually different inference of this primordial helium fraction. So what do we learn from this is that basically the moment you include the IL polarization from the cosmic microwave background, this option is not a viable option to solve this discrepancy. The other thing we try is to modify the early time expansion history by tweaking the parameter of the effective number of neutrino species. But effectively what this does, it changes H, the expansion rate, before recombination. And again, you find that in order to solve this tension, you will need basically half effective neutrinos. But the moment you add the Planck IL polarization data, then this option is also disfavored. So then let's try to leave the early universe physics the same and change the late time cosmology. So let's try to do an S-spline reconstruction of the expansion history. We parameterize the Hubble as a function of redshift with few knots in S-splines, and then play the game of the direct and inverse cosmic distance ladder. And you start playing this game by mixing and matching data set. Let me just use H0 and supernovae. And then this is basically saying, yes, it looks a lot like a lambda CDM, but just with a different H0. Then let's add H0, baryon acoustic oscillation, and a measurement of the sound horizon radiation drag. The measurement of the sound horizon radiation drag has a smaller error bar than the measure on H0, so the fit says, forget about the H0 measurement, revert to a Planck cosmology. And you can mix and match and see what happened. Basically, the upshot is that the shape of the expansion history is very well constrained. Even though you try to reconstruct it in a model-independent way with S-splines, the data will allow you maximum 5% wiggle around a lambda CDM. In overall, shape is much, much less. The issue is with the normalization. Remember, each ladder needs 2 good anchor points. We have a very stiff ladder, but the 2 anchor points don't agree with each other. So we can transform the H0 problem in a sound horizon radiation drag problem. And this is the plot that we managed to do back in 2016. So by doing a non-parametric reconstruction of the expansion history with all this data, we can take the H0 measurement and transform it into a sound horizon and radiation drag measurement. Here it is from the local measurement. And this is the inference from the actual measurement from cosmic microwave background. So you see the mismatch. The mismatch is less statistically significant than the previous one because now this has been done in a model-independent way, while in the previous plot it was in a lambda CDM model. So a paper came out last week, which was entitled Sound Discordant. So they do exactly the same, but with slightly more recent data, and then they do forecast for the next generation CMB data, and this is their plot. So a collection of data set combination and the value of the sound horizon and radiation drag. These are inference from the local measurement of H0, and these are measurement from the cosmic microwave background. So you see the mismatch, it's still there, and it's the same statistical significance. So for those who want to wait, standard sirens eventually will come to the rescue. So we have seen there was a LIGO Nature paper last fall where with one event with electromagnetic counterpart, they could make an Hubble constant determination with still a relatively large error, 14% error, but this was just one event. The moment you have 15 of those, then this kind of measurement could break the tide and say, which Hubble constant, it's correct. So let me back up a second, and you can say, excuse me. You can say, excuse me, because cosmic microwave background measurement entangle early plus late time information. So when I tell you that the cosmic microwave background measures the sound horizon and radiation drag, in most analysis, this is done assuming a model, typically a lambda CDM model or a variation on the lambda CDM model. And in this, there is, since you see the last scattering surface across the entire universe, there is information there about the evolution of the entire universe. So the information is all mixed up. This is the power of the cosmic microwave background. That's why we can learn so much about the universe. But the moment when you want to deconstruct the model and separate early time from late time because this end-to-end test you think may have failed, then this is a problem. So I don't want to spend a lot of time on this because it's relatively technical how you actually implement it, but there is a way to analyze cosmic microwave background data that marginalize or take away the information about the late universe and only is sensitive to the information about the early universe. So this is, so the original idea was proposed in Oden et al. Collaboration in 2012, but we've implemented it on the Planck first data release last year. And the question that is relevant for this talk is, can you constrain the sound horizon and radiation drag in a way that is independent of what the universe does after the last scattering surface? The answer is yes. The price you pay is that you can't use class and CAM the way they come out of the box. You have to open them and do something to them. And in particular, you have to throw away the information at the low multiple because they are affected by the integrated Sachs-Wolf, which is an early time, it's a late time effect. You have to marginalize over the position of the peaks because that's the geometry of the universe, which is again something that goes between the last scattering surface and you. You have to marginalize over the overall amplitude because the overall amplitude mixes two information, one about the primordial universe, the amplitude of the primordial power spectrum, but the other one is about the late universe, which is the integrated optical depth to the last scattering surface, so you need to marginalize over this. And you need to take away the information that comes from lensing, which on this plot produces smoothing of the higher order peaks of the cosmic microwave background, but you can do that by going into the gravitational potential and marginalizing over that in the code. But you can do that, and the answer is yes. And If you leave standard early time physics, the answer is this one for the sound horizon radiation drag, 147 plus or minus 0.34. The error bar actually don't grow much with respect to the standard analysis, which is quite good. It means that this quantity is not sensitive to the late time physics. You can also do that by relaxing the assumption about early time physics. You can throw in some complicated model of matter, some complicated model of dark energy. It's relatively robust to that. What is not robust to is if you put some complicated model of radiation. Say, if you mess around with the amount of radiation that is in the early universe, if you assume some extra dark radiation, if you assume some extra neutrino species, and then this, the error bar around this quantity gets bigger. So in a nutshell, for this first part of the talk, the H0 problem is an anchor problem. Either a redshift equals 0 or a redshift 1100, which cannot be solved by tweaking or bending the expansion history. It can be solved by changing the sound horizon radiation drag, and therefore early time physics, but the polarization data impose some tight limits on what you can do about the early time physics. So the Hubble trouble is a mismatch of anchor. There is no evidence for a strange expansion history. You can shift H0 or RS. You want to keep this in mind if you are looking for new physics. About half of an effective neutrino would do if there is no Planck polarization, but better data are coming in. So I want to go back to this paper that came out late last week that is called Sound Discordant. They say, so if you want to look for new physics, involve new physics, you need to find a new early universe physics that changes RS by 7%. That is not easy. The other way you can do, you can say, let me leave the early time physics the way it is, but find something else that changes the way that sound horizon radiation drag gets imprinted in the baryon acoustic oscillation. Say a velocity bias. So although you could put some velocity bias in, some researchers have explored that, you can't get to 7%. I mean, you can get to 7% if you break the LCDM model, but you know, at that point, if you break the LCDM model, you can break it in many other ways. So whatever you do, therefore, must affect the 2 decades of scale factor expansion immediately prior recombination. If you do it much earlier, there's no effect. If you do it much later, there's no effect. That's where your change needs to be. If you change things after a combination, it gets really complicated because you want to keep consistency, for example, for the omega matter determination that you get from the position of the first peak and matter radiation equality and things like that. So, but new CMB data with polarization will be crucial to actually probe this and give us some clue of whether there's something going on there or, you know, the early universe physics, it's the way we think it is. So let me move on and talk about the second possible surprise or bet that we can do where we may find surprise in cosmology. And I want to talk about the cosmic neutrino background. So that's a relic of the Big Bang, similar to the CMB, except that it decoupled for matter 2 seconds and not 380,000 years after the Big Bang. So at decoupling, neutrinos are still relativistic, and they have a large velocity dispersion, and that's their effect. Now, of course, there are in here many more neutrino hitting us that come from the sun than from the cosmic neutrino background, but the cosmic neutrino background pervades the entire universe, while the neutrino that come from the sun decayed as you go away, and the universe is very big. That's why on cosmological scales, it's the primordial neutrinos that matter, but locally they don't. So what's a neutrino for cosmology? It's something that behaves like radiation at recombination and decoupling, eventually possibly becomes non-relativistic, and it behaves like matter, has a small interaction, although we'll not talk about those here, and has high velocity dispersion or is hot. Now, it doesn't necessarily need to be a neutrino, but if you had to match something that has this property with a particle that we know of, then it would be a neutrino, if you see what I mean. So regarding this, Planck 2018 has spoken. It says, I take from the paper, the presence of a light thermalized stellar neutrino is in strong contradiction with cosmological data. the production of stereo neutrino possibly explaining some particle physics anomaly would need to be suppressed by some no-standard interaction or no special mechanism. So there are some tight constraints about how many effective number of neutrino species you may have. And this is to link with the previous talk, number of effective neutrino versus the Hubble parameter, the Planck prediction, and the direct measurement here. So we see the H-naught trouble again. So, but what I want to talk about is that cosmology is key in determining the neutrino absolute mass scale. So in this plot, I have the mass of the lightest neutrinos versus the sum of the three masses. For here, we assume three neutrinos, right? And then here are the oscillation constraints that tell you you have to be either here in the inverted hierarchy or here in the normal hierarchy. So this is called degenerate, this is inverted, this is normal. Up here, it's forecasted performance of the Catherine experiment. This is, a terrestrial experiment that wants to measure neutrino masses. Of course, it doesn't measure directly neutrino masses, so this prediction is a little bit model dependent because it depends on the coupling angle. But the forecast, it's taking data, are here. Where is cosmology? CMB Planck primary plus BAO, 95% limit is here. 2018 CMB Planck plus lensing plus BAO plus polarization brings you down here. Order of magnitude already below forecast from a terrestrial experiment. Forecast live here. Now, there are two things to take away from this plot. The fact that there is a floor over the sum of neutrino masses means that neutrino contribute at least to 0.5% of the total matter density. In the era of precision cosmology, this is potentially measurable, and indeed, all the next generation of surveys have in principle the statistical power of actually detecting the signature of neutrino mass in the sky, provided that systematic error are kept under control. Here we are looking at sub% effect, so the name of the game is systematic error. The other thing you want to take away from this plot is that as this line moves down, the inverted hierarchy starts being a little bit disfavored. So somehow cosmology, although cosmology is not really sensitive to flavor and things like that, can tell you something about the hierarchy, and therefore the mechanism to give masses to the neutrinos. So how does it work? Well, neutrino mass above 1 eV means that the neutrino become non-relativistic before recombination, so the effect is seen in the cosmic microwave background. Total mass below 1 eV become relativistic after recombination. You can still see it in the cosmic microwave background, but the effect can be cancelled by degeneracy with other parameters, and so that's the degeneracy. You have to add extra information to that. And the information you want to look for, it's information that come after recombination. And the information is that finite neutrino masses suppress the matter power spectrum on scale smaller than the free streaming length. And this is linear prediction for the matter power spectrum. And it's the ratio between the power spectrum for massive neutrinos and power spectrum for massless neutrinos. If you keep fixed omega matter h square, omega baryon h square, and lambda, this is 0 neutrino masses, this is 0.3 eV, and this is 1 eV. Now, cosmic microwave background we have seen from Planck when they add the lensing information tell you a constraint that is much better than that. It's almost an order of magnitude better than that, but because it adds information that come from the late universe, not just the primordial universe. It adds the lensing information and it adds the BAO information. So let's go back to that in a second. The other thing that you may want to keep in mind is that if you squint, here you see some effect. That is, that different masses become non-relativistic at slightly different times. So in principle, cosmology can yield information about the neutrino mass hierarchy. In reality, it's not exactly the hierarchy. It's the splitting, the mass splitting, but that's related to the hierarchy. So before we go on, you say, oh, wonderful, this is a very big effect. It's a depression of the matter power spectrum on small scales, which is exactly what large scale structure test. Look, this is a 20% effect. I should be able to see that. However, one should be a little bit careful, because if you now move along the cosmic microwave background parameter degeneracy, you play again with H. H is everywhere. Now you keep fixed omega cold H square, omega baryon H square, and the position of the first peak. And then the plot that before was this dotted line now becomes something like that. So you really have to be careful where you look for your signal. But still, the effect is there. You have some effect on the baryon acoustic oscillation, you still have some change in the power spectrum, and you still have some effect on large scales that is due to this mass splitting. So before we go on to that, let me show you some constraints. So you want to include large scale structures clustering to go after the real price, which is the neutrino mass, because the pros is that you can see the signature of the scale-dependent clustering suppression. The cons is that there is astrophysics, there is bias, there are non-linearity. This is traced by galaxy. Galaxy trace the dark matter in a complicated way, so there's all that. So a possible approach that the community is taking, and we also took in our group, and a useful exercise is to use completely different tracers and see if they agree. Then if they agree, a lot of this, it's probably below your error bars. So what we did a couple of years ago is to use red galaxies, blue galaxies, and another group has been using the Lyman alpha from the BOSS survey. And in summary, what we find that you have an upper limit 95% of the sum of neutrino masses below 14 eV, which is insensitive to the choice of galaxies. If you believe luminous red galaxies that have a little bit more statistical power, this goes down to 0.13 eV. If you look at the combination of cosmic microwave background plus baryon acoustic oscillation plus Lyman alpha, you get down to 0.12 eV. Planck 2018 full, including Lansing and BAO, gives you an upper limit that is completely consistent with that. So this relies on Lansing. So completely different tracers, different systematics, different biases. They all agree with each other. This also makes you think that past various claims of detection of 0.3 or 0.4 eV neutrino mass doesn't hold. They were probably based not solely on data set, which I call AAA ratings. The interpretation of every data set, I think, should get a rating, like the credit rating for countries. I come from Italy, I live in Spain, I know quite a bit about credit rating. There are some observations that are easier to interpret. There are some observations that are more difficult to interpret. That's the credit rating. So where does this leave in this plot? It leaves that we're here. Which means that whatever is down here gives you a 5% or less effect on the matter power spectrum. We are looking for percent or sub-percent effects. If I add in this analysis the H0 local determination, which is, we know it's inconsistent and we shouldn't, but if we do, then basically the inverted hierarchy starts really being out of favor. So let me go back on the hierarchy effect on the shape of the linear matter power spectrum, because I think that's important and it connects to the systematic warning that I was giving you before. I say neutrino different masses have different transition between relativistic to non-relativistic behavior, and their individual masses and mass splitting can change the detail of radiation domination to matter domination regime. So a few years ago, we came up with a parameterization in terms of this big delta, which amplitude tells you basically the mass splitting, and which sign gives you the hierarchy. And so if you plot the sum of neutrino masses versus this parameter delta, the oscillation will tell you that you can be here if it is normal hierarchy, and here if it is inverted hierarchy. Look, these lines don't extend to, to zero, because there is a minimum neutrino mass floor. We've seen it in the oscillation, and which is different in the inverted hierarchy and in the normal hierarchy. And then cosmologists start excluding this part of parameter space and cutting this plot in this way, right? So you see that the moment you get a neutrino mass constraint or even measurement, that you have only two values for delta available from the oscillation. And if you want consistency, you should go and measure this delta and check that you get the same. So how would you do that? So this is the effect of a change in delta on the linear matter power spectrum. You see it's a relatively large scale, so linear theory is fine. This was for different masses that were still available when we came up with this plot. This still, now we really need to go to smaller masses, 0.1 or 0.06 eV. That's where the effect is. It's a small effect, but in principle, there's enough statistical power in the sky to see that. So in my view, this will offer a powerful consistency check. If you measure a delta that doesn't, if you measure a neutrino mass, then you can go and read the delta you would expect. Then you go and measure that delta. And notice that the signal come from completely different scales. The neutrino mass comes from relatively small scales. The delta come from large linear scales. So the systematics are different. And you find a value of delta that does not match with any of the hierarchy, then you should not blindly believe the mass measurement. Probably you have not measured neutrino. You have measured something else. However, if the two measurements match, then that offers you some extra confidence that you've really seen neutrinos in the sky. So before we go on, let me say something else about the neutrino mass determination, because over the past year, there was at some point some alarm saying, actually, no, you can't measure it, even if you have statistical power and you don't have survey systematics and you understand nonlinearity and you understand Ricci space distortion and you understand everything, because there are biases that come from neutrino bias. What do I mean by neutrino bias? So first, by bias here, I mean halo bias. Galaxies live in halos. Halos don't trace exactly the dark matter distribution because they are, the peak of the dark matter distribution, and therefore they are bias tracers. But it turns out that if you define the bias with respect to the total matter, called plus baryon plus neutrinos, this halo bias acquires a scale dependence that depends on the neutrino mass itself. So here's the game you wanted to play. I want to look at the scale dependence of the matter power spectrum traced through the galaxies or the halos to see the neutrino mass. But now the neutrino mass itself gives you an extra scale dependence, so I cannot disentangle these two things. So, between 2 years and a year ago, everybody went, we can't really measure it because of this effect. So, we decided to ask ourselves, first, is it a problem? 2, can you model it or get rid of it? Is it a problem? First, note that the bias defined with respect to the cold plus baryons, not cold plus baryon plus neutrinos, does not have this issue, does not have this extra scale dependence. So the overall amplitude still depends on the value of the neutrino mass, but not really the scale dependent. The overall amplitude depends, but not the scale dependent. So you can write things down how this bias, now defined with respect to the cold plus baryons, it's related to the matter. And then you say, let me break this quantity, which is scale dependent and neutrino mass dependent, in 2 bits. There is a large scale, which is a scale independent part that depends on neutrino mass. But there is a scale-dependent part that does not, and therefore I can compute it at neutrino mass set to 0. And I compute it at neutrino mass set to 0 because I will need to calibrate this on n-body simulation, and it's much easier to run an n-body simulation for 0 neutrino masses than for massive neutrinos. So I can do that. So that's what we did with Alvise in last year. And then the second question we ask, is this a problem if we ignore it completely? Because now we quantify the effect. And the answer is, so we plotted a lot of these forecasted error ellipses. I don't want you to understand exactly what that is. It's just not much for current survey. For current survey, you can ignore it, but it's comparable to statistical error for future surveys. So it's a problem for future survey. So we say, okay, here's some useful fitting formula and a prescription to compute this quantity. So you can go and run with it. And then the next question we ask is, why should you worry? Why worry when you can correct for it at very little extra cost? So the idea is to get fit for BCC numerically, but no need to explore different neutrino masses. The neutrino masses primarily affect the amplitude, so large scale bias, not the shape, but we can calibrate that. So with a graduate student, David Valchin, we decided to come up with an emulator. It's called Be Happy, which basically gives you BCC for all neutrino masses. And also, this quantity is a key for modeling Redshift space distortion, because in Redshift space now, the key quantity is this bias, not the bias as we always know it. So our idea will be to calibrate this massively on n-body simulation done for you, and then give you a class plugin, and then you forget about the problem. It's just already accounted for. So in the last few minutes, I want to give you another possible bet, if you're a betting person, of where the surprise may be. So the end of this second part is that the surprise may be that in the next generation survey, we will see the signature of neutrino mass in the sky. And then we will have an estimate of the overall neutrino mass scale, which terrestrial experiment cannot give you. And we've seen the beginning of multi-messenger astronomy, and here I want to say something about multi-messenger cosmology. So this is a very quick summary of a paper that it's accepted, maybe also published, that was led by a master student, Guido Scelfo, and Nicola Bellomo, who is sitting here. So every difficult question about this, you can ask Nicola, who was the driving force behind this project. So the idea goes as follows. In a not too distant future, we will have maps of galaxies. We have those already, but also maps of gravitational waves events. So far, there are very few, but eventually, and we plot them here with their error ellipse as they will be determined in the sky. So each of these it's an event with their error ellipse for localization. So you wait a few years and you start filling this up. And then eventually, you can make a low resolution map of this distribution. And then you say, wonderful. Are the black hole mergers, as we see in gravity wave signal, of stellar or primordial origin? Because these are the big questions that we are asking after we've seen that all these mergers seems to be around 20 or 30 solar masses, and the stellar route was maybe more likely expecting something else, or maybe not, but black hole could be a dark matter candidate. There is a whole discussion of in which mass range, could it be the whole dark matter or only a fraction? Let's be agnostic. So how would this work? So in big halo, if you have primordial black holes, they will not merge because the velocity dispersion is really high, so they will pass through each other and they will not really merge. But in small halos, where the velocity dispersion is lower, eventually they will, and then they will release gravitational waves, and let's assume that therefore statistically the one we see are those. How small? Small. Small means that they really probe the dark matter distribution and they don't probe the massive galaxies distribution. On the other hand, if they are of stellar origin, they are where the stars are, so they are where the galaxies are, and not in the low density region and the filaments that are traced by very low mass halos. So the idea of that paper is to say, why don't we do a cross correlation between a galaxy catalog and a gravitational wave map? So if you do the cross correlation and you end up finding a match like this, then you say they're a stellar origin. If you do a cross correlation and you find out that it's something like that, it's much more likely of primordial origin. So that could be another possible surprise, maybe. So let me conclude because my time is almost up. So I talked about the H0 tension, and I would like to report two quotes. One is by Rocky Kolb, who said that the H0 tension may be the next disruption in cosmology, but also I would like to put that next to another quote by Carl Sagan, who says extraordinary claim needs extraordinary proofs. And I don't think we yet have extraordinary proofs. There's a lot of more work to be done, but it's being done. On neutrinos, they are 3, and their sum of the masses is below 0.13 to 0.12 eV, and this measurement has been done in several different ways. This places the inverted hierarchy under pressure. How much pressure depends on how you define your priors. And I don't want to open that Pandora box, but you can ask me and we can discuss. Forthcoming galaxy survey can in principle detect the sum of neutrino masses in the sky, but the name of the game is systematics, and having consistency check, I think it's really important. Finally, multi-messenger cosmology is now a reality, and is probably a treasure trove for both known physics and expected physics and unexpected physics. And I show you one example, but surely there's a lot more. And I'll stop here. Thank you.
Since I'm a beginner, I'll ask a beginner's question after your very nice talk. The standard model of cosmology can be reduced to 6 parameters, but you can also allow extra parameters up to about 20.
Yeah.
So fitting any data set, you have a question of priors and a question of constraints. So I was wondering, naively, if you allow these 20 parameters, and there might even be, I'm sure people can think of more than 20, okay, is it possible to add as a constraint the local H0 measurements and see whether you can fit the data, allowing some of the parameters like maybe flatness to not be flat, etc.
So people have tried to play this game, and with the usual suspect of those parameters, the one that can do something about it, are the primordial helium fraction and the number of effective neutrinos. All the other one, the one that are in the standard expansion of the lambda CDM model, don't work. Of course, you could imagine coming up with something really weird, that is an expansion history. With what I show you about the constraint on the shape of the expansion history, it's an S-spline reconstruction. Assume it is smooth. I haven't tried, and as far as I know, nobody has tried to put in there an expansion history that is not smooth. And then you could imagine actually very close to you, where you have no BAO, to do some very quick transition of dark energy so that H0 becomes very large. So this goes in the direction of actually saying we live in a local void, and therefore the local measured number of H0 is not the global one. But if you do that, you really throw the lambda CDM really out of the window, because that void will need to be so deep.
Deep and big, because we have SN data pretty far out now.
So exactly, so you have to make it small enough so that you don't affect the supernovae, because the supernovae looks fine. They don't show any sharp transition, right? But deep enough so that you explain that 7% mismatch. So yeah, there is a question from the back, I think.
About the local void,
yeah.
essentially, because you didn't talk about, for instance, there could be some problem with the Cepheid measurements or the observations from Tom and those people who are talking about the 150 H inverse megaparsec local void.
Okay.
As I understand, it seems that quite unlikely. You have to do more stuff with the CMB that I didn't fully understand in order to have that explanation. And I guess you have to also throw out the cosmological principle.
Yeah, yeah. So there have been some studies trying to quantify how big the void needs to be to explain this mismatch, and how unlikely is to find that in realization of a lambda CDM-like universe. It's extremely unlikely in a realization of the lambda CDM universe, so unlikely that you would have to throw the lambda CDM out of the window. So there are many ways to throw the lambda CDM out of the window. One could be the local voids, one could be changing RS. We have to explore that. So,
but there are some observations which seems to indicate there may be a local void.
okay, so all these observations are based on light. And there is a gap there, right? A big uncertainty on how you map light into the actual dark matter distribution. I mean, what will worry me, that I don't know if anybody has looked at, is that if you have a local void, at the edge of the void, the velocity are going to be very high. So that should give you a kinetic SZ, and that kinetic SZ should give you an imprint in the cosmic microwave background. We have seen some kinetic SZ in the cosmic microwave background, but it's very small. So my question is, if there was that void, would that kinetic SZ be so big that we would have basically seen by eye and we haven't seen it? And I don't know the answer to that, but maybe people that work in Planck have looked at it.
Yeah, I don't think that constrains this particular problem, but I think the papers on the void claim it's like looking at a very small region of the sky, and as you say, it's based on light, so yeah, I think it's... And yeah, there is a paper where they try to fit for like a very rapid expansion, like with an exponential in dark energy, but it's like completely ad hoc models. Any other question? I have many, but we can discuss later. Okay. If not, thank you very much, Licia.